In this video, we're going to discuss algorithms and operation counts, and this will allow us later to compare the different implementations of the simplex method. An algorithm is just a finite set of instructions written in any type of programming language. Our goal is that of being able to compare algorithms without the need to implement them in a specific programming language. The way we're going to achieve this goal is by counting the number of arithmetic operations performed by the algorithm. Here, it's fundamental to understand what we mean with the number of arithmetic operations. For us, arithmetic operations are additions, subtractions, multiplications, divisions, and comparisons. In particular, every arithmetic operation is independent on the number of digits of the numbers that take part in this arithmetic operation. For example, if we sum 2 plus 2, this is one arithmetic operation because it is just one addition. If we sum a million plus a million, it still is one arithmetic operation. This implies that the number of arithmetic operations that we count is not necessarily realistic. However, we do this for two main reasons. The first is that it simplifies greatly our analysis. And the second reason is that even if we did consider the number of digits in each arithmetic operations, then the results would be essentially the same. Later on in the course, at the very end, we're gonna get back to this issue of the number of digits in our numbers, and we're gonna discuss this in much more detail. But for now, just remember that we only count the number of arithmetic operations and we don't care about the number of digits in the numbers. So let's see immediately some example. Let's say that we have two vectors a, b in Rn and we want to compute the inner product A transpose B. So what is the definition of inner product? A transpose B is A1 B1 plus A2 B2 and so on and so forth until plus AN Bn. So in order to compute A transpose B, we need to compute the n products A1 B1, A2 B2 until AN Bn, and then perform n minus 1 additions to sum all of them. So the total number of arithmetic operations is 2n minus 1. In our second example, we're going to look at matrix multiplication. Here we have two matrices A and B of dimensions n times n, and we want to compute the product C equal to AB. Now we know very well how to compute the product of matrices, namely the entry ij of the product matrix C is obtained as the inner product of the ith row of A with the jth column of B. We already know that performing the inner product among two n vectors requires 2n minus 1 arithmetic operations. To obtain our matrix C, we need to perform such an inner product a total number of n squared times, because we need to obtain every entry Cij for every ij from 1 to n. So the total number of arithmetic operations is n squared times 2n minus 1. We have just seen two examples of two very simple algorithms, and we have computed the exact number of arithmetic operations that they perform. The next thing that we want to do is, in a sense, simplify this number of arithmetic operations, because we don't really care about the exact number of arithmetic operations. Instead, we only care about how fast it grows with respect to the input. For example, in the case of the inner product, we saw that the total number of arithmetic operations is 2n minus 1. However, for us, it's not so important this minus 1. Of course, you can imagine this minus 1 has essentially no impact for large values of n. And we also don't really care about the 2, because between 2n and n, again, the difference is not so important for large values of n. So essentially, we want to simplify our life, and the takeaway from this number should only be that the number of arithmetic operations performed by the inner product increases linearly with n. For matrix multiplication, the total number of arithmetic operations was n squared times 2n minus 1, and this number of arithmetic operations is equal to 2n cubed minus n squared. In this case, we want to summarize this number by just saying that the number of arithmetic operations performed in matrix multiplication increases cubically with n. Now that we've understood what is our target, we're going to introduce the definition of big O and big omega that allow us to achieve our goal in a formally correct mathematical way. In this definition, you should think of f of n as the exact number of arithmetic operations performed by your algorithm, and you should think of g of n as the simplified rate of growth, which is essentially the takeaway from the complicated formula f of n. Then let's see this definition. Let f and g be functions that map positive numbers to positive numbers. We write f of n is equal to big O of g of n if there exist positive numbers n0 and c such that f of n is upper bounded by c times g of n for all n greater than or equal to n0. So essentially this definition of big O tells you that f of n is big O of g of n if for large enough n and up to a constant, then f of n is upper bounded by g of n. Next, we have the definition of big omega, and it's essentially the same thing. The only difference is that while big O is used to obtain upper bounds, big omega is used to obtain lower bounds. So we write f of n equal to big omega of g of n if there exist positive numbers n0 and c such that f of n is greater than or equal to c times g of n for all n greater than or equal to n0. So the only difference is that instead of big O we have big omega, and instead of less than or equal to we have greater than or equal to. Let's see a few examples. If the function f is 3n cubed plus n squared plus 10, then we can say that f is equal to big O of n cubed. As an exercise, you should prove that this is actually correct. And the only thing you have to do is to find the n0 and c which work for this example. Similarly, n log n is equal to big O of n squared, and n log n is equal to big omega of n. If your function f is a polynomial function, like in the first example here, then it is very easy to obtain the corresponding g function. In fact, you only need to pick the monomial of the highest degree, in this case 3n cubed, and drop the constant. In this case, you obtain exactly n cubed, which is your function g. As an exercise, you can prove that this procedure always gives you the function g of n, such that the original function f is big O and big omega of that g. Another simple trick is that log n is always big O of n and big omega of a constant. Once you have shown that this rule holds, then you immediately obtain that these two examples are correct. From now on, when we talk about the running time of an algorithm, we mean the number of operations performed by such an algorithm. Of course, the running time of an algorithm may depend on the specific input given to that algorithm. Of course, we are not interested in understanding the running time of an algorithm for any possible input. What we want to do instead is to estimate how the running time increases as the input becomes larger. For example, in the case of linear programming, we might be interested in estimating how the running time increases as the number of variables and constraints increases in our linear programming problem. In particular, this means that for a specific number of variables and a specific number of constraints, we want to obtain a unique running time, which is a little bit strange because there are many possible inputs that share the same number of variables and constraints. So how can we do this? And here there's a specific choice that we can make. The choice that we make is that among all the possible instances with that number of variables and that number of constraints, we pick the worst case, namely the input with the longest running time. This is a very conservative measure, of course, and instead you could, for example, consider the average among all of these instances with the same number of variables and constraints. Each approach has its advantages and disadvantages. One advantage of the worst case analysis that we perform is that it gives us an important guarantee that for any possible problem with that number of variables and constraints, then the running time will be lower than the one we're considering. On the other hand, the downside is that this worst case analysis can be, in some cases, too conservative. In fact, if you think about it, if you have 1 million possible inputs with a specific number of variables and constraints, and only one of them has a very, very large running time, while all the others have a very, very small running time, then in our analysis we will select still the worst case, so the one with a very large running time. In this case, of course, our analysis will be very, very far from the average, because if you select randomly one input with this number of variables and constraints, with high probability you will obtain one that has a low running time. And so in a sense, our analysis will be very far from the average one. Personally, I think that both the average runtime analysis and the worst case runtime analysis are of equal interest. However, in this course, we're only going to deal with the worst case analysis. And the main reason we're going to do that is that it is much easier to analyze. Later on in this course, I'm going to get back to this topic, and we're going to see some intrinsic difficulties in understanding the average running time for the algorithms that we will be looking at. Now let's see another example of running time. We consider here a system of linear equations. So the problem is the following. We are given a matrix A that is n by n, and we're also given a vector B in Rn. What we need to do is either compute a solution to the system of equations Ax equal to b, or decide that no solution exists. We all know how to solve this problem. In fact, the standard algorithm to solve this problem is Gaussian elimination, which eliminates one variable at a time. It is well known and it is simple to show that this algorithm requires big O of n cube arithmetic operations. And I suggest that as an exercise you work out this running time. For this problem, O of n cube is also the runtime for more advanced practical methods. So while there are ways to improve on Gaussian elimination, the running time remains O of n cube in practical methods. So let's keep this in mind because we're gonna use this many times. The first takeaway from this slide is please remember that Gaussian elimination requires big O of n cube arithmetic operations, because we're gonna use this several times later on. But the next question I want to pose to you is this running time O of n cube good or bad? What I want to convince you of in this slide is that essentially this running time is good. Of course it will be good because we will later compare it with something that has a running time that is much worse and which will be our bad running time. In this slide I will not be very formal, I just want to give you an idea on why we essentially think that this running time is good. Essentially what I want to show you is that this running time allows you to solve problems of twice the size every constant number of years. So now let us forget about big O to simplify things and just look at n cube. So if the runtime is n cube, we're essentially saying that to solve a problem of size n, it takes n cube operations. This means that if you want to solve problems of double the size, you will need 2n cube operations. Now 2n cube obviously is 2 to the cube times n cube. This tells us that the runtime of problems of size 2n is 2 to the third times the runtime to solve problems of size n. Let's say that at this point in time, we are able to solve with our computers problems of size n. Then Moore's law tells us that in 3 years, more or less, our computers will be faster by a factor of 2 to the 3. Therefore, in 3 years from now, we will be able to solve problems that have size 2n, so double the size of the problems that we can solve today. Of course, this argument doesn't really depend on the 3 in the running time, but you could replace 3 with any constant c. Then the takeaway of all this discussion is that roughly every c years we can solve problems of twice the size than earlier possible. Now algorithms with a runtime of big O of n to the c for some constant c are said to run in polynomial time. And these are the algorithms that we consider good, because essentially they scale very well with time. As time passes, the algorithms quickly become more and more powerful. Things go very differently for the algorithms that are called exponential time algorithms. These are algorithms that have running time omega of 2 to the n, where again n represents the problem size. So these are the algorithms that we consider bad. And in order to understand that, let me figure out how long we need to wait to increase only by 1 the value of n of the problems that we can solve with a specific algorithm that is exponential time. So once again, let's consider the runtime as 2 to the n without the big omega. Now, if instead we consider a problem with the value n plus 1, the runtime will be 2 to the n plus 1, which is 2 times 2 to the n. And of course, 2 to the n is the runtime for a problem with size n. So this tells me that to solve the problem with n plus 1, we need double the problem of size n. And again, by Moore's law, such a factor of 2 will be achieved after essentially 1 year. In this argument, we consider the runtime 2 to the n, but you can easily see that a very similar argument can be applied if you have a runtime of the form 2 to the cn. What you would obtain is that for algorithms with runtime big omega of 2 to the cn, every c years we can increase the value of n that we can handle only by 1. So to recap, in polynomial time algorithms, every constant number of years, the value of n that we can handle doubles. While in exponential time algorithms, every constant number of years, the value of n that we can handle can only increase by 1. So it is reasonable to expect that no matter how long you wait, problems with truly large values of n will always be difficult to handle with exponential time algorithms. Now let's see an example of an exponential time algorithm against a polynomial time algorithm. Let's say we have two algorithms. One has exponential runtime, and specifically it is 10 to the n over 100. And the second one is polynomial, and the runtime is 10 n cube. Interestingly, for very small values of n, for example n equal to 3, in this case the exponential time algorithm is better. We can see that by just substituting n equal to 3 into the two expressions of the runtime. For the exponential time algorithm, we obtain 10 to the cube divided by 100, and this is equal to 10. And for the polynomial time algorithm, we obtain 10 times 3 to the 3, and this is 270. Of course, 270 is much larger than 10, so the exponential time algorithm is better. However, we don't really care about small values of n, because essentially any algorithm can quickly solve problems that are very small in size. So let's take a little bit of a different approach and see how big are the problems that we can solve with our two algorithms by waiting 1000 seconds, which is essentially 17 minutes. Our computer is a workstation that can execute 10 to the 7 arithmetic operation per second. So the total number of operations in our 1000 seconds will be 10 to the 7 times 1000. Now that we know the total number of operations that we can perform, we obtain for each algorithm the corresponding n that achieves that number of operations. For the exponential time algorithm, we need to solve the equation 10 to the n over 100 equal to 10 to the 7 times 1000. And if you solve this equation, you obtain n equal to 12. Therefore, in 17 minutes, we can solve problems with n equal to 12 when we use our exponential time algorithm. On the other hand, with the polynomial time algorithm, we need to solve 10 n cube equal to 10 to the 7 times 1000. If you solve this equation, you will obtain that n is equal to 1000. So in 17 minutes, our polynomial time algorithms can solve problems with size 1000. Clearly, 1000 is way larger than 12. So the polynomial time algorithms allows us to solve much larger problems. And this difference between the two will only grow the more time you let your algorithms run. All my discussion about computational complexity so far is very basic, but at this point I don't want to give you more details. My message at this point is that roughly it is useful to consider polynomial time algorithms as algorithms that are fast and efficient, and we should think of exponential time algorithms as algorithms that are instead slow. Now this is everything we needed to introduce and compare the different implementations of the simplex method, and we're gonna see them in the next video.